and welcome to our webinar with the interesting topic Identifying Anomalies in Production. My name is Melanie Bellmer and I'm very pleased that so many of you are taking part today. We have two experts for this topic in the studio today. Firstly, I would like to welcome Mr. Patrick Kaiser very warmly. He joined the EMAG group 2 years ago and works as a data scientist. Secondly, we have Dr. Andreas Kühne with us. He works as a lead data scientist at NEURON, our strategic partner in the area of data analysis and artificial intelligence. And Patrick and Andreas will guide us through the webinar today. Now I directly give the floor to Patrick and wish you a lot of fun with our webinar.
Yeah, thank you, Melanie. Welcome to our webinar on anomalies during production, identifying problems and potential for optimization in production processes with machine data. To begin with, some introductory words. Nowadays we have the situation that the technical potential of modern production facilities is almost exhausted or has almost reached its limits. However, there's still optimization potential of production lines available, for example, caused by unexpected machine or tool breakdowns, unobserved quality problems, or inefficient production processes. Today, by means of digital technologies and especially the emergence of IoT, we gain access to machine and production data at any time in the process. AI and data-driven solutions make use of this data and enables to detect deviations from normal or expected behavior at any time. As a result, this helps to fully utilize the production potential and gives a huge competitive advantage. Before we dive deeper into our today's topic, we first have to clarify some terms related to anomaly detection, in case you don't know them already. At the very top, we have AI. AI mainly deals with recreating structures of human intelligence, for example, reasoning or perception. Within AI, we have the topic machine learning, which is about programming in computers in a way so that they can learn from data. Within machine learning, we have various approaches, and one of it is anomaly detection, our today's topic. But what is anomaly detection about? Anomaly detection mainly deals with detecting unexpected behavior. The idea behind it is that we want to model and forecast expected behavior and detect deviations from it. On the right, you can see an example showing the actual numbers of users of a website and the predicted ones. And you can see here two anomalies where the actual number of users is far higher than the predicted ones. This is considered an anomaly. The reasons in this example could be an attention-getting social media post, which led interested users to the website. Now I hand over to my colleague Andreas, who will cover the topics monitoring of production KPIs and anomalies during production processes. Afterwards, I will go on with anomaly detection for predictive maintenance.
Thanks, Patrick. As Patrick suggested, we are now going a bit from the theory more into practice. So how you could use anomaly detection methods to make use of them in practice in the production to leverage your full optimization potentials. Within this topic, we will have a look in 3 different areas. First of all, we look at monitoring of production KPIs. Then we go deeper into the production process, what you can use anomaly detection in there. And last of all, we continue with predictive maintenance approaches. To start with, first of all, we want to introduce the common KPIs that are used in productions in order to analyze production efficiency of production plants and lines. So often we talk about the cycle times or the takt time of each individual part. This should be fine. The part count is obviously very important, and also the target part count within a shift, for example. The quality and rejection rate of the parts, and also the machine downtime is often measured and analyzed. And one of the most important factors in production is obviously the OEE. Often these factors are analyzed only per shift, per day, or per within a week maybe, and not in a great detail. But what we want to show you now in the next few slides is that if you go deeper and analyze them in more detail, you use, for example, on top AI-driven methods, then you can really use also these KPIs to identify problems or optimization potential in your production line, and leverage this to optimize your production processes. So we, as EMAG, we already have some software tools that can help you to calculate these KPIs directly from machine data. So we offer different data apps that, for example, calculate the part quantity and also make a part quantity forecast, so which will you achieve within the shift with the different production speed. We have an OEE calculation monitor, and we also have like tools that directly calculate the cycle times. At the current stage, for example, we can visualize the data from these apps in dashboards, so that a worker in the line can directly see these effects and has his transparency on about his behavior, and can react, for example, if the production speed is too low. And this is also a good interface to kind of alarm different anomalies in production processes.
We have our first question, Andreas.
Perfect.
Do you also offer systems which analyze anomalies live and take actions immediately?
Yes, so these apps which we just discussed, we use machine data to directly calculate KPIs first. And in some of these apps, for example, a cycle time monitor, we also can have the potential, or we can directly identify anomalous takt times. For example, if the production process is too slow. And we didn't do it yet in the process, but with dashboards and also with smart devices, we could alarm those so that the worker could react, or maybe also a worker could react and see what's wrong in the machine. So yes, we are there already. Yeah.
Thank you.
Okay. We have these apps to calculate KPIs, but on the next step, the question is, what kind of anomalies are we expecting in practice? So there are different types of KPI anomalies that we are expecting. For example, there could be obviously spontaneous events, which could be OEE drop down when you have a tool breakage or a machine breakdown, then the machine stands still. Obviously, your OEE goes down, so it's like a one-time event. But you could also have like one-time systematic events. Meaning, if, for example, a worker is changing the program of the machine, or you have an adaptation of your automation system, you can either improve your productivity, or in some cases you can also, the productivity can decrease. And often this also remains unobserved because the changes happen in such a small detail that nobody can analyze it and can detect it without data analysis methods. Another thing which we are expecting are repeating systematic events. This could be, for example, through scheduled maintenance during a week. This could be, for example, caused by shift changes, by breaks, by shop floor meetings, and this could all have an effect on productivity. And some fourth example of a pattern that we might expect or can maybe observe are systematic trends. It could also occur in KPIs, to be honest. For example, if you have accumulating problems in an automation process. But most of the time, such a pattern we expect actually when we talk about machine wear or tool wear, when some accumulating process lead to increasing damage, then something like this is expected. And what our goal now is that we identify these patterns in the KPI data and with advanced analysis to identify optimization potential. To give you a start of how this could look like in practice, we want to go deeper into cycle or takt times. What you can see on the top right is, for example, the cycle time distribution or the cycle times of each individual workpiece of a producing machine. And you can see most of the cycle times are quite similar, with some deviations in the positive or negative direction. But there is also one very strong anomaly. By eye, this is very easily identifiable. But in practice, we want to have some algorithm that automatically detects this and this anomaly and maybe sends an alert. So what we do in this previously mentioned cycle time app, we train a statistical model which, based on the machine data, automatically calculates the expected takt time and also the expected deviation of the takt time. And when we have this, we can apply it again on our measured data in the live system, what you can see here. So for example, we have here now our expected takt time and the area of deviation which we expect. And now all the takt times which are moving in we find in between, we don't have to worry about. But if we find the takt time outside, then it could be some important issue which maybe might be necessary to be alarmed. For example, in this case, there could be no parts available.
Where is the data used to train the model from? How big has to be an anomaly to be detected?
The data for these the data apps we just discussed is coming directly from the machine. So it's collected by the EMAG IoT gateway, the EDNA Cortex. So we calculate the KPIs directly from the machine data. In theory, we could also use KPI data from, for example, MES systems or something else, but this is how we do it. The second question, how big is an anomaly to be detected or to be also important? This is a question where I cannot give a clear answer, because in practice it's like this. So you have some statistical measures, and there is very easy to identify an anomaly in the statistical means. But in practice, a statistical anomaly might be not relevant. So often you need to have a combined set of rules, like combining statistics and expert knowledge to tell when should be an anomaly alarmed or not. And this is how often in practice these systems are implemented.
Perfect, thank you.
Okay, very good. Okay, so then let's continue with the slide. So what I just talked about is this one-time or spontaneous event. What we also can see in a second on the upper right is that we also, this system, or especially in particular for cycle times, we can also identify one-time systematics events, and this might be even more relevant to be alarmed. For example, what you can think of, a worker went to the machine and changed a parameter or modified the override and forgot to move it back. Then the cycle time might be a bit longer than expected. If nobody realizes that and the shift produces like this all the time, then in the end of the shift we have a significant number of parts less. So there it would be really important to feedback this alarm back into the process so that somebody could react and adapt again. For example, if the feed override is changed, like we see in this example. But we can not only use anomaly detection to do live analysis of, for example, cycle time or other KPIs. We can also use it to analyze historic data. For example, what we did here, we took the cycle time data of 7 individual machines in a production line and looked at the distributions of cycle times that are normal, meaning expected, which we see in green, and cycle times that are not expected, meaning anomalous, here in red in this graphic. And then what we did, we looked what happened in the machine when we had anomalous cycle times, meaning too long cycle times. And what was very interesting, that in this case, one of the most occurring alarm what we had in the machine was that the machine was waiting for new workpieces, or like that the workpiece is getting caught by the robot for the next machine, or that some new workpiece is arrived to be produced. And this is something where now a worker or a production line manager could go and think of how can we, for example, improve the automation process, that there is with buffer bands or different programming of the robot, that this is not a bottleneck in the production process, and thereby he or she could leverage the production potential. With this, I want to continue with the next KPI, which is maybe the most used KPI in production, the OEE. So what you can see here is the OEE of over a day of production with the individual shifts, and you see what we calculated here is the OEE in the last half an hour. And what's quite interesting here is that it's obviously not constant during the production process, but there are some drops, there are some highs, and it's changing continuously. To analyze this a bit more systematically, we took the data over the last 2 months and calculated what is the average expected OEE in these individual time windows. And interestingly, the OEE is quite good, but interestingly in the night shift it's already higher than in the early shift. Could be because in the early shift maybe there are some more shop floor meetings so that the production facilities stands a bit longer, but you can see some systematic effects. But on top, when you now compare the OEEs of the individual weeks, which we did in the gray lines here, then you see that some weeks they produce completely fine, but some other weeks like these have these outliers where the OEE drops significantly. And this seems to be also a pattern. It's not like a random occurring during the day. And when you look deeper, then this pattern is that you have an OEE drop in shift, often in shift changes, and an OEE drop in breaks, which could be also expected, but whereas there's also some potential for optimization.
We have our next question.
Okay, perfect.
Which factors influence the OEE the most, except for breaks and shift changes? Which of them can be analyzed and improved?
Yes, also a good question. A question where there is not a clear answer, because I think it depends clearly on the production process. In this case, we saw that some more process-driven events like shift changes or breaks have a strong effect. But obviously any effect or any potential in the production should be somehow seen in the OEE, because it comprises all the different factors from quality to availability of the machines and also the throughput of the machines, or the productivity. So any effect you should see in the OEE, but in a second step, often what you would need to do in practice is you need to analyze more other KPIs maybe and dig deeper. So make a diagnosis where the origin is. And in theory or also in practice, it could be changes in the program, could be problems with the automation system, could be problems with the material quality. So, but it's a good starting point to identify there is a problem, and from there you can start a diagnosis.
Okay, thank you.
Okay, then let's go back to this example. What we did next, after we identified there are significant OEE drops during breaks and shift changes, we want to identify what is the potential to, like, what kind of effect could we have on the productivity if we change those. So what we did here is we analyzed on one thing, we analyzed how many parts we lose during each break on average, but also how many parts we lose during shift changes. And there we saw some interesting effects, that during shift changes, often shift changes run very smoothly and nothing happens, so the production is continuing and we have no loss in productivity. But sometimes we have also like breaks of 20-30 minutes over shift change, and we lose up to 20 parts, and this is quite significant. On average, we calculated 3.2 parts we lose during each shift change, and 1.5 parts during each break. If we sum these up for the complete line, it's about 3,500 parts we lose for the whole year, and this is kind of 1% of the total production capacity of this line. And if you think about it, like if you just adapt maybe slightly your process, so you have maybe overlapping shift breaks, or like you tell your workers that they have to prepare the tools, or make a tool change earlier than the shift break, and so that your production line could continue over the shift break or the shift change, for example, then you could already achieve a significant increase in your productivity. To wrap this all up, this topic, monitoring of production KPIs, how can you get this into your process? And what is also key in our point of view is that you not only do these analysis that we showed you now, or calculate the KPIs and do the analysis, but to get this back in practice. So for example, for a spontaneous event, if you have AI solutions to identify them, what's really necessary that you can alert or have some alerts or can warn somebody, so that you, for example, have smart devices, have dashboards, have it connected to your HMI at the machine, so that the worker can react and maybe do something and fix the process again. If you identify more systematic problems, then obviously you have to have an expert that looks at the historic data of your KPIs, identify some problems and optimization potentials. Then you have to have certainly some discussion rounds where you think of what are the actions that we want to take. And then you can also move it back in, put it back in your process and kind of benefit from these analysis of your KPIs. But overall, with these analysis and with these feedback loops between machine data, analysis system, and your process, you can benefit and improve your productivity just by analyzing your KPIs in depth. Okay, from this, we want to go from KPI data now more to the what's happening in process, like in the process of one part. And there, anomaly detection also could play a significant role in future. So obviously during each process a lot of things and a lot of sporadic problems can occur. So for example, you can have increased tool wear, more increased than you expect. You can have tool breakage. You can have part quality issues that are unexpected. You can have increased machine wear and downtime. And this could be caused by several things, again, by different materials, change parameters, and so on. But if you don't detect them in time or like in process, then you can have severe problems. Because, for example, if you have part quality issues, then you can throw away maybe the parts of a full shift. So that's why it would be very beneficial if you could monitor your production process and have some data-driven or AI solutions to identify these unexpected problems and react accordingly. And to show you how this could look in practice, we have one example that we went deeper or that we implemented actually within the last year with an EMAG customer. So what the problem was there, that there was a problem with thread cutting in a machine which caused not okay parts. The diagnosis showed that there are some random and transient failures in the Z-axis linear motor which were not easily fixable. What this made the customer do is that he had to manually control all parts and measure the diameters, and this obviously had some significant costs because one worker only had to do the measurement of all the parts. So the idea here was that we implement a data collection system and also an AI algorithm to have a data to out of the data identify these not okay parts which are only very sporadically occurring and also remove them from the process. To achieve this, we did 3 individual steps. So in the first step, we needed to get the data from the machine. For this, we used the EDNA IoT Core and the EDNA Cortex as an IoT gateway, and also implemented a specific sampling interface that was able to collect high-frequency machine data. This was necessary because in the previous slide, I quickly mentioned it. These failures in the Z-axis linear engine was only very transiently, so 20 milliseconds. So the normal frequency was not enough, which we could get. So we had implemented this high-frequency sampling interface. With this system, we started collecting data from the machine, and after we had data from 1 or 2 weeks, we started to develop an AI algorithm. The AI algorithm had the goal to identify these not okay parts based on this machine data. So what we did in the first step, we needed to identify each individual cut of the thread cutting because it was 12 repeating cuts. So this we did with a segmentation approach, which you can see in the left side. And from this, we got the data of each individual cut. In the next step, we calculated the velocity of the Z-axis and looked where there were anomalies in the velocity and quantified the strength also of these anomalies, which here is shown in the red signal. And then in the last step, we developed a machine learning model that was able to identify based on these quantified anomalies okay and not okay parts. And this information or this AI solution we then installed directly at the machine. So we now had the machine that was producing. We had also the IoT gateway that was collecting the data, the high frequency data, and then the AI solution directly in process analyzed the data of every part, made a prediction if the part is okay or not okay, and gave the signal back to the IoT gateway. But now the last and maybe most important step was to also get the information back into the process so that the worker could react. And for this, we installed, we also implemented a way back to the machine control. So what's happening now, if the algorithm identifies a not okay part, the part is excluded from the process automatically. The worker is alarmed by an additional light which was set up in the machine, and he now can kind of confirm that there is a part excluded in the HMI and start the process again. But like this, we made sure that all not okay parts were removed from the process and the manual measurement was not necessary anymore.
How reliable does anomaly detection work? Do you guarantee certain detection rates?
Yeah, thanks. Also a good question, which also there could be not a general answer to this question. So in this case, what we just showed now, we had a very good detection rate, meaning we did not miss any not okay part for this specific problem, which was necessary to kind of get rid of the manual control. So this was very good. In other cases, we have to see that then this needs to be discussed. How difficult is it to identify the problem? Let's say if it's a very specific problem or specific anomaly, the detection rate is for sure way higher. If it's a non-specific one, then let's say the detection rate will get better with feedback, which I also will talk about now in the next slide. So maybe I get back to it.
Okay, thank you.
Okay, thanks. Good. So as I said, this was now a very specific example for an anomaly detection within a process. In general, such a system could be very, very beneficial because, as mentioned in the beginning, there are a lot of different and sporadic problems, but which can have a lot of costs and cause a lot of problems and also costs within the production. So therefore, what could be a general solution is that with the IoT gateway, we collect different machine control data and also sensor data, and then develop an AI algorithm which matches the data for each workpiece and also which includes an anomaly model. This anomaly model must have the capability to represent the good data of a workpiece. And then having this capability, it can identify which workpiece is okay and which workpiece is not okay, and give this again back to the machine, for example, to the HMI or a dashboard to smart devices. But what's now key here is that we also need feedback. For example, if we say there was just an issue in the production process, please worker have a look, then it would be necessary that the worker also gives feedback. Yes, this was a problem or not. And this could be, for example, directly implemented with an HMI. On top, we think would be quite beneficial if there's also a second layer feedback where, for example, an expert can have a look into the recent anomalies that were detected by an algorithm, can say yes or no, this was a really anomaly, what was the cause? Okay, we had a tool breakage, we have a parameter change, we have some material issues, and what was the effect? We had some quality issues, we have tool breakage, increased tool wear or crashes. And with this information, if you feed this back to the algorithm, then we can always continuously run model updates so that the algorithm gets better and better, gets better detection rates of anomalies, but can also start diagnosing which anomaly could have which effect, maybe quality issues, crash, or something else. But in practice, this could be a system which could be very beneficial, and it's certainly something that will be seen in future.
Can anomaly detection be used for automated process optimization?
In theory, yes. I think if, for example, anomaly, like a specific anomaly, for example, in part quality is identified and you can fix it with changing a parameter or correction value, then you could do this. But in practice, I guess we are at least 2 or 3 steps away from this, so that, for example, anomalies get detected and the AI algorithm directly steers back and the machine and automates the machine. There are some specific examples I know that are working in practice, but a general solution doesn't exist.
Okay.
With this, I also want to close these first 2 topics and give over to Patrick, who will talk about anomaly detection for predictive maintenance.
Yeah. Thank you, Andreas. To begin with, when do we refer to predictive maintenance? Normally, we can perceive 4 different strategic approaches to do maintenance, which can be classified by the dimensions maintenance intensity and cost. The green curve here depicts the downtime costs, and the red one the maintenance costs. The turquoise one shows the combined costs where we can range these strategic approaches. As you can see here, to get the lowest possible combined costs, a company has to aim for predictive maintenance. In addition, the slide here shows the importance of choosing an increment of predictive maintenance based on the customer's need. The reason for this is simple. The higher the increment value, the higher the complexity of implementation. For example, if a company only wants to know if the machine is healthy or not, as it takes own measures, probably assessing the health condition of the machine is enough. On the other hand, if the company wants to know the point in time to do maintenance, it probably should go for the last increment. However, this largely depends on the availability of data and it's not always possible to get the last increment value here. As an application example, I will now expand on our EMAG AI-based solution, EDNA Health Check. This product allows, on the basis of vibration measurements, the assessment of the machine condition. We call it health condition, in reference to machine components, for example, the feed drives. To do so, sensor data is collected from every machine and then analyzed by our cloud application. As shown here, the first step of the EDNA Health Check is the assessment of the measurement. So a measurement is made, of course automated and on a regular basis, for example, once a day during lunch break. After that, the health check process is carried out. That is the analysis by our AI algorithm and supported by our EMAG service expert knowledge. But more info on that in a minute. And the last step is the health check results, visualization in this case, to relate the results to historical data in order to detect trends, for example. But I will also come back to this in a minute.
What is required to install such an analysis system?
Good question. To install our EDNA Health Check, you need, of course, the vibration sensor. In this case, we call it the NEURON 3DG. And as a basis, our IoT gateway consisting of the EDNA IoT core and the EDNA Cortex.
Okay, thank you. And can you also tell where does the algorithm run, in the cloud or on a local PC?
The algorithm runs in the cloud.
Perfect, thank you.
Okay, then I will go on with the next slide. So, as I already mentioned, first of all, a measurement is made. After recording this measurement, the algorithm applies a so-called automated segmentation step, as can be seen here, in order to get the single segments, for example, the segment for the feed test in X direction or the spindle test. And these segments are then analyzed individually in the next step. Now, the main part of our health check algorithm is called into action by feeding the algorithm with historical and expert labeled training data or measurement data. Ideally, this data consists or represents a broad range of different conditions in terms of health or machine wear. And this historical data is then used to determine the allowed deviation from a good data pattern, which was modeled beforehand, as shown here as the dashed line. This modeled good data pattern normally represents a condition with no vibration at all. After that, we can relate or map the calculated deviations, we call it in this case feature values, to corresponding health values by fitting a so-called health function, in this case a sigmoid function, as can be seen here. This is the so-called health function, a sigmoid function. This means basically the higher the deviations, expressed here as feature values, the lower our health value, our calculated health value. This fitted health functions or models can then later on be adapted to single machine types or single machines with further historical data. In the end, we can use these generated models to get the health condition of the machine's axis and visualize them, for example, in a line chart, as can be seen here. In this way, we can detect possible trends, which may indicate a critical machine state and provide recommendations in such cases.
How are conspicuities or anomalies detected in the health line chart?
So right now we are applying a 3-level monitoring. So we look for an absolute threshold, for example, here at probably 20% health. And if we exceed this health limit, so there will be an alarm for our service experts. We can also check for the trends, for example, over the last 5 measurements. We can say if the health decreases about 2% on average, this maybe is an conspicuity and we have to look deeper into it. Or we can also compare the prior predictions or the prediction from yesterday, for example, to the current prediction and show if there's an deviation from, I don't know, 20%, for example, and we will have an alarm in this case.
Okay, thank you. And can you also tell us who evaluates the results? Does EMAG support here?
That's a good question. I will come to this in my next slide. The health check is triggered automatically and in process to minimize cost and effort. And our EMAG service experts are also getting notified about the results and provide assistance, for example, by offering diagnoses. So to answer your questions, we largely depend on the knowledge of our service expert who can go deeper with who can elaborate on our algorithm results and offer, for example, diagnosis, as I already mentioned here.
Perfect.
And to summarize here, so we also use this feedback from the service to further improve our algorithms. That's
Okay, and we have another question. Okay. How long does the process take from notification to diagnosis?
So normally we talk about minutes. However, if we have a very complex case where the service experts has to go or has to offer an in-depth diagnosis, this will take a little bit longer. So on average, we talk about 30 minutes from notification to diagnosis. Yes.
Okay, perfect. Thank you.
So let's go on. On the next two slides, I have some real-world examples which took place at our pilot customer. The example here shows a substantial drop of the x-axis health at about mid-July to early August. This can also be seen here in our vibration pattern. As it turned out, this was an indicator for a broken ball screw, which led ultimately to the failure of the x-axis feed drive. And after replacement, the health value increased again, as can be seen here by this vibration pattern again. So the the second and last example here shows how we can also use the algorithm and its results to specifically support our EMAG service experts in making diagnoses and fixing found problems. We also had a case at our customer that showed that the spindle health was on a rather moderate level. To find the cause, we also looked at the measurement in the frequency domain, as shown here. And we were able to detect a so-called inference frequency. This inference frequency, or more specifically the corresponding frequency band, can also be detected by our algorithm automatically. And our service expert can then use this information from our algorithm to apply, for example, a spindle optimization. This was also done here in this case at our pilot customer. And after spindle optimization, the health value increased again, and the inference frequency was also gone if we look here at the measurement in the frequency domain.
We have our next question, yes. Patrick. In which cycles will the algorithm be updated? What about the update policy? So
the update policy largely depends on the machine type or the machine. So do we have enough data for this machine? How good are our models already? Therefore, I can't fix it on a certain number. But the main advantage of our cloud application is that we can deploy updates very fast and quick, so we do not have to be on-premise at our customer to apply updates in this case.
Okay, thank you.
So yeah, and this brings us already to the end of our today's webinar. Here on this slide, we have summarized our 3 key learnings for today. The first one, unobserved spontaneous events as well as undetected systematic deviations from optimality have a significant impact on the productivity of a plant. The combination of IoT infrastructure and modern AI solutions provide the basis to automatically detect deviations and thereby rapidly identify errors and deviations from expected behavior. And the integration of such anomaly detection solutions with the plant processes and, of course, the employees is a key to leverage the fully potential of anomaly detection solutions.
I hope we could convince you that anomaly detection or data-driven methods and IoT solutions can help to identify potential in your production lines and also to leverage them. As EMAG offers already different building blocks and solutions, for example, the EDNA IoT Core, the EDNA Cortex as kind of IoT gateway to collect your machine data, EDNA Lifeline dashboards and data apps to analyze and already calculate your KPIs and already identify anomalies there and show it in dashboards. And also obviously the EDNA health check. But on top, we also are readily available to develop custom solutions, just like shown with this process monitoring for detecting not okay parts. And so we are happy to talk about custom solutions with you that are tailor-made to your challenges and needs. And with this, I want to thank you for your attention and your time.
Okay, yeah, thank you very much, Patrick and Andreas. And for you, welcome back. And I think we already have the first question. How big is the implementation effort for existing and new machines?
For new machines, the effort is not that big. So it's just a checkbox in the configuration for the machine. However, so if we look at existing machines in the field, it depends on the machine type and has to be checked at our customer.
Okay, good. The next question. What is the price range for such a system and machine?
This depends on what is exactly needed. For example, we start with the EDNA IoT gateway and with including the IPC and installation, we range between 7,000 and 9,000 euro per machine. Depends also if a sensor is included for EDNA health check or not. The EDNA health check service costs about 3,000 euro per year, including diagnosis by EMAG service. So it's not only the software, also the service on top. And the data apps are around 500 euros per machine per year. But if we get to more complex solutions, this is all on individual pricing. But yeah, if you're interested, just get in touch.
Perfect, thank you. So let's see if we have another question. Yes. We don't have data analysts. Can the system also be used by non-specialists?
Of course, it can be used by non-data analysts. For example, we build our web apps in a way so that it can also be used by non-experts.
How does anomaly detection react to changing parameters?
This depends on the model and how it's implemented. For example, what's often done in practice actually is that the model is continuously training on new data and user feedback, and like this you can easily adapt to changing parameters. If you have some particular changes, for example, in the production program, you could also implement a system that that a user can either say, okay, change and train the model newly because we have a new process, or the model detects that there's a new production process and then starts training new. So there are different ways of doing it, but in practice it has definitely to be considered because otherwise you run into big problems.
Okay, I think this was the last questions. Here you see again the contact details of Patrick and Andreas, and you are of course very welcome to contact us there. We have now reached the end of our webinar and hope that you were able to take some interesting impulses with you. We would like to thank you once again for your participation, also in the name of our 2 experts here in the studio. Take care and maybe until next time.